Hello, hello. Welcome back to another installment of complex numbers. Today we're talking about arithmetic in the complex plane. Don't forget this capital C with a bar for the complex. And specifically, the most important thing for us today that we're going to learn is what we call the multiplication law, and you'll see what that is. Our mindset message today is find the beauty in math, specifically patterns. There's a really cool point we're going to make here today. In that the way we view things matters and might make things much simpler if we just shift our perspective or the way that we are looking at it, okay? And we'll see that as we go through. Learning goals specifically represent complex arithmetic graphically, aka geometrically, such as adding, subtracting, scaling, multiplying by I, just I. But then the main thing, especially with this multiplication law, is we're going to represent full multiplication graphically and see what that does and what it means. Your prior knowledge today would just be performing arithmetic with complex numbers by hand, and that would be like adding or subtracting, multiplying them, and stuff like that. And just graphing in the complex plane, making sure you're familiar with where to place a complex number and how to put its vector from the origin, okay? And that brings us to our first point here. Important thing to start out today, I want to remind you, there are two main ways to represent a complex number, okay? And we can represent it as a point or as a vector. Now what we've typically done up to this point is we've kind of drawn the point and then put the vector to it, right? But technically the vector itself can be said to represent the complex number, or the point itself could be said to represent the complex number. And there are advantages to each one. So as a point, we typically just think of it as x plus yi. As a vector, it is literally the visual directed arrow starting at the origin that we draw in. So I suppose it'd be helpful if I keep those axes in there, okay? So if this was the vector, if we had a point, right, x plus yi, so this could also be said to be that complex number, okay? When is a point useful? We know that working as points, that's what we've mostly spent our time doing. It's quick and efficient, especially doing calculations, or if we have equations solving, like when we solve the quadratic equation, right? And if it had no real solutions, it has complex solutions. When you're square rooting a negative, right? And stuff like that. So it makes a lot of that stuff simpler and easy, right? Graphing something can be long and tedious. But when we think of it as a vector, you're actually going to see that today we'll look at something where it's more efficient to view it as a vector. A vector specifically visually represents magnitude and direction. So that's one thing that's important, because you know that the magnitude is the literal length of the vector, and the direction angle, aka the argument, is the angle from the positive x-axis, right, that vector is rotated at. And it really helps us not just do arithmetic, right? So to actually do the arithmetic as a point is easier. But to actually understand the arithmetic and how it works, vectors are very helpful. So that's what we're going to jump off on today. So as you probably gathered, our focus today will be shifting to vectors. So we've been working with points, we're now just going to be focused on vectors. Now I have three reminders. There's three theorems that we learned in Algebra 2 with graphing complex numbers, and three specific operations: adding, scaling, and multiplying by I. So just only by I. So these are the things that should still be in your notes though, again. So a reminder, the sum of two complex numbers, okay, so when I say C's, that means complex numbers, forms a parallelogram. And that's kind of crazy. So what we're saying here is, if this was Z and this was W, then if you add Z plus W, it's always going to be in between the two. And furthermore, if you actually finished connecting the tips of each of these arrows, this result would actually form a parallelogram. We're not going to prove it now because it's not that big of a deal, but we have proved in the past why that's true. And the cool thing is if you place this z up here and this w, they have the same magnitude and direction there, which is essentially why it forms a parallelogram. Quick side note, subtraction is just adding opposites. So I didn't mention subtraction, but that's because if we had two complex numbers, let's say a plus bi, and we're subtracting c plus di, it's the same as taking a plus bi and adding negative c minus di, right? You kind of just distribute that negative in there. So it all just falls under that same rule of adding. Our next rule that we've learned in the past with vectors and complex numbers is that scaling alters magnitude but not direction angle. Except when the scale factor is negative, then it's simply a 180-degree rotation. But they're all in line with each other. Now, this is just something, again, to think about. And this should be intuitive, actually, to you guys. This green one, z, is my original vector. If I multiply z by just a single real number, so no imaginary, just like scale it. So let's say we took, for example, let's say we had a complex number 3 plus 5i, and if I multiplied it by 2 to get 6 plus 10i, right? This is what I'd call my scale factor. So just a single real number that's multiplied into the whole complex number. So if that k value, okay, that's what we're calling our scale factor. So in this case, our k is 2. If it's greater than 1, of course it makes sense that it would lengthen our vector. If you're multiplying by a number that's between 0 and 1, like 0.5 or something, you're going to reduce the length of your vector, right? The magnitude. And then if it happens to be negative, what happens is the vector just points in the exact opposite direction, which is why I say we rotate it 180 degrees. But then after that, it could lengthen or shrink depending on the absolute value of k. Okay, so those are some important things. Again, notice that the angle did not change at all. It's only the magnitude that was affected by a scale factor. And then the last thing we've learned in the past, multiplying a vector by I rotates 90 degrees counterclockwise. And that's kind of a crazy thing. This is something we'll spend actually a moment talking about. Let's see what this looks like. Maybe it could be like, I don't know, 5 plus 2i or something. Let's say we took 5 plus 2i and we multiplied it by I. What happens is this becomes 5i plus 2i squared, and we know that that's negative 1. So actually, this becomes my real part, and that's now my imaginary part. They kind of switch roles with each other. But this becomes a negative 2, and then plus a 5i. If you were to think of these as coordinates, though, as we have in the past, you know, if you should have learned in geometry class that if I had 5 comma 2, and I switched these, and then I made the 2 negative, you have learned in the past that when you do this, it makes a 90-degree counterclockwise rotation. And so it's essentially the same effect here. Okay, but again, there's no change in the magnitude. It simply rotates it by 90 degrees. So let's just get a little bit of practice just putting that into practice. And then we'll jump into our main thing with full-on multiplication, because each of these pieces will factor into how we make sense of multiplication. So just to get a little bit of review and practice, why don't you go ahead and look at these two complex numbers, z and w, and represent each of the operations here graphically. What I want you to try to do first is simply just draw the graph and more or less approximate or estimate how to do it graphically based on the rules we just talked about a second ago. What you can do after that, if you'd like, is you can actually perform the arithmetic purely with the points given, right, with the actual numbers, and then plot it and see, see if you got it, okay? So go ahead and pause right now, and then we'll take a look at it. Let's see how we did here. Now, ignore the final result here for now, and maybe you already calculated it, but if we just were to place z and w, remember that z plus w is between, but it must form a parallelogram, okay? And if you just think about w, for example, right here, remember how this is down 5 and it's over 3? Well, then from here it's going to be down 5 and over 3, right? Because you remember that is identical across, okay? So there's z plus w, and then sure enough, if you add the pieces, 6 plus 3 and 2 plus negative 5, and we get 9 minus 3i, and you can see that that fits. Okay? For b, what do we expect to happen with 2w? It just becomes twice as long in the same direction, right? So if you graph w, then you know it's going to be twice as long in the same direction because we just scaled it by 2. And again, you can confirm that by doing the multiplication, and you can see 3 minus 5i becomes 6 minus 10i, and that matches, you know, our gut intuition about that. Now C and D, I've kind of combined two things at once, sort of. This has a scaling, but also a reflection, I guess, or we said it goes the opposite direction. So if z is this, then the 1/2 is going to make it half as long, and the negative goes in the opposite direction. So that's exactly where it becomes, and you can see that if this was 6 plus 2i, this is half and negative, so negative 3 minus I. And you can see that's still in the same line. You can even check that they have the same slope as each other. 2 over 6 is 1/3, and then up 1 over 3 is also 1/3. And then last, this one's a weird one too. When we multiply by I, 90-degree rotation, right? But then also the 2 makes it twice as long, and that's exactly what happened. If you look at W here, he rotates 90 degrees counterclockwise, but he also becomes twice as long. And sure enough, if you actually perform the calculation, you get 10 plus 6i, and you can see that that happened. Let's go ahead now and dive into full-on multiplication if I have two full complex numbers that are in the form x plus yi, like 2 plus 6i or something